All right, this is our first video. These are a great way for you to look through the notes, go through the content of the course, but also giving you an opportunity to go back, speed things up, slow things down, check your notes so you have them and you have the explanation along the way. So, all right, here we go. We're going to first talk about sunlight and seasons. And this is important because without an understanding of how these two work, we can't really visualize how ecosystems are built and why we have certain areas of higher productivity and certain areas of lower productivity, which pretty much set the grounds for the entire ecosystem development. So we're going to start with this. Just as a quick refresher for you, the sun is our primary energy source for all life and, very important, weather as well. It is going to convert nuclear energy into heat by a process called fusion. So thermonuclear fusion, we're going to take a bunch of hydrogen, turn it into helium, and that's going to release so much energy. So much energy that has been doing this for the last 5 billion years and will continue to do so for quite a long time as well. But the most important piece here is that it is our primary energy source. Because of this light energy that's leaving the sun, and because Earth is quite far away from the sun, we are 151 million kilometers away, we're only going to reach 1/1000th. Only 1/1000th of its energy is going to reach us. So this is important. We're not getting all of the energy, but we are getting 1/1000th of it as it comes into Earth. So when it arrives on Earth, it's going to come to us in visible light. Then it's going to convert into heat, and this heat is going to create wind, weather, and ocean currents. So that's the majority of the energy is going to turn into that. However, we do have 1% of the light energy that's going to convert into the food energy. So our plants are going to take 1% of it and convert that into food energy, which is the basis for all of life. So let's talk about how we're going to measure energy. Energy is measured, I'm going to make sure we highlight it. Energy is measured in joules. Extremely important that we remember that. Another unit that we are going to primarily talk about here is watts. Okay, watts. So here's your equation. 1 watt is 1 joule per second. This is kind of a rate unit here. So watts talk about how much energy is being received per second. When the sun strikes Earth, and very important, this is at a perpendicular angle, we're going to talk about that later, we're going to get 1,300 joules of energy per second, which is equal to 1,300 watts per square meter of surface. So this is what we're looking at here. 1,300 watts per meter cubed. This is a solar constant. So the important thing here is that both the energy and time, but also surface area, all three of those play into how much energy is reaching this planet. So very important that we remember that guy. Okay, now that amount of light is all dependent on the angle of the light, the angle that the light is hitting us. So we consider this kind of the surface density of the light energy. It's greatest when it comes in perpendicular. So this here is an example of perpendicular. So it's coming in at a 90-degree angle to the earth, to the land. So when we have this, it is the greatest. But most often, it is coming in at an angle such as this. So we're getting it coming in at an angle. And when it comes in as an angle, it's going to decrease the amount of light energy received. Those watts are going to decrease. So here's an example here. If I have 1 meter squared and we're coming in at a 90-degree angle, we're going to get 1,300 watts per meter squared. However, if the light is coming in, if you notice this is the same wattage here. If the same amount of energy is coming in at 2 meters squared, it's going to spread over a greater area. So now I've got 1,300 divided by 2 meters squared, and we're going to get a smaller amount of energy that surface that each meter is receiving. At the equator, light's going to come down at a steep angle. So when we say steep, we're talking about something like 90 degrees. So because of that, it's much more concentrated, and we're going to get more watts per meter squared, and it's hotter. So one more time, because we have a steeper angle, it is more concentrated, there's more watts per meter squared, and it's going to be hotter. Now this is contrast to the poles. Light's coming at a lower angle. We're talking closer to maybe 30 degrees. So it is much more spread out. And because it's more spread out, we have a larger meter squared, so that light's going to be shared over we're going to get fewer watts, and therefore it's colder. So this is just an example, kind of walking us through this. The closer to the equator, the more light energy, and so there's more energy available for photosynthesis, and therefore we have more biodiversity. So this is talking about latitude versus the amount of kilowatt hours that we get per day. So you can see the latitude would be our north-south lines. So the farther north or the farther south we go, these will be like the poles down here, they're going to have a lower number of isolated energy. Where up top here, this would be the equator, we're going to have higher amounts of isolated energy. And all of that creates these seasonal variations in temperature that are a result of the fact that most importantly, Earth is rotated at 23.5 degrees. This is a very important number here. So because we have this rotation in the orbital path, the angle of the light is not always going to be 90 degrees. Most of the time, it's going to have different angles, which are going to create different temperatures. Okay, so during the summer, this is a great diagram here. I really like this diagram. During the summer, Earth's axis is tipped 23.5 degrees towards the sun. So this X here, we could say represents Korea. So if we're talking about summer, we're going to spend some time talking about summer here. You can see that we are tipped toward the sun, 23.5 degrees towards the sun. And in winter, over here, we're tipped 23.5 degrees away from the sun. So as you know, when it's summer in the northern hemisphere, it's winter in the southern hemisphere. So because it kind of flops. If it's summer up here, that means we're tipped away here on the bottom. Now we do have some solstices, and this kind of gives us an idea of how we are in this, how we are with our connection to the sun. So if I have a June solstice, which we're going to say in the June solstice for us, the South Pole is tipped away and the North Pole is tipped towards the sun. However, in the December solstice, it's the opposite. The north hemisphere is tipped away, the southern hemisphere is tipped towards the sun. Whenever we have a solstice, the area that is tipped towards the sun is going to have a longer day, and the area that's tipped away from the sun will have the shortest day. Now, we also have what we call equinoxes. And so at these equinoxes, the poles are neither tipped towards or away for the sun. So actually what's great is that on these days, it's the only 2 days in the year where we have 12 hours of daylight and 12 hours of darkness. So that happens on these equinoxes twice a year. Now, this is not something that you probably pay attention to, but the height of the sun in the sky is also based on this tilt. So again, we're bringing back this 23.5 number. During the summer solstice, it's going to be 23.5 degrees higher than the equinox. And then in the winter, it's going to be 23.5 degrees lower. So this is a great diagram here that talks about how the height of the sun in the summer versus autumn versus spring changes, and it's all related to this 23.5 number. So all of this different tipping and angles and amount of sun energy is what creates our different biomes. And more importantly, it helps us really differentiate between the tropics and the Arctics. So we're going to start with this important one. The tropics are the regions of Earth that are located within 23.5 degrees, again, that number comes back again, of the equator. So our tropics are going to be from here all the way to here. So 23.5 degrees north and 23.5 degrees south. So all of this within here would all be considered our tropics. Most of the time, or not most of the time, but 2 days a year, they're going to have the sun directly overhead them at noon. Now, this is very different from the Arctic and Antarctic, which is going to be the 23.5 away from their poles. So anywhere from here to here and here to here. So within these regions, they will get 24 hours of daylight in the summer, and they will get 24 hours of darkness in the winter. But again, we're looking at this trend of how 0 to 23.5 are our tropics, and then 90 to minus 23, too far. 90 minus 23.5 are the Arctics, the Arctic and Antarctic. And so all of this variation creates different amounts of daylight at the latitude. So we have some different examples here. So if I have this is 66.5 degrees north, we're going to get some massive changes. Where if you're actually the equator, you're not really going to experience any changes at all. Because of this amount of light, we're going to get most life. Our highest abundancy in life is going to be in the tropics because they're getting more sun. It is more direct. And remember, more direct means more watts and kilowatts. And the days are not short. So because they get more sun energy, they have longer days, and they have more direct energy because of the angle. All of this is going to lead to an increased overall kilowatts that are received in total, leading to more productivity. All right, I think that's it. Please let me know if you have any questions.